Hello one and all, welcome to another online video by Einstein Academy. Today we'll begin talking about the third topic from the JCH2 chemistry syllabus, topic on the gaseous state from the JCH2 chemistry syllabus. Okay, in particularly, we'll first look at the first two learning outcomes from this topic, learning outcome A and B from the gaseous state. Okay, so learning outcome A, candidates should be able to state the basic assumptions of the kinetic theory as applied to an ideal gas, as well as to explain qualitatively, in terms of intermolecular forces and molecular size, the conditions necessary for a gas to approach ideal behavior, as well as the limitations of ideality at very high pressures and very low temperatures. Okay, so let's begin. I'm going to begin discussing the topic on the gaseous state by first talking about the kinetic molecular model of all the three states, the solid states, the liquid states, and the gaseous state. This is usually not taught when going through this topic, but I would like to discuss this because I would like to explain why is it that at the JC level, we only learn about the gaseous state. Why do we not have a topic called the liquid state? Why do we not have a topic called the solid state? But specifically, we have a topic called the gaseous state. So before I can explain that, I first have to talk about the kinetic. I first have to begin by talking about the kinetic molecular model. Okay, so as we learned previously in lower levels, matter exists in three states: solid, liquids, and gases. In the solid states, the particles are very closely spaced. In the liquid states, the particles are further apart, and in the gaseous state, the particles are very, very far apart. Moreover, in the solid state, the particles are arranged in a regular and fixed at their lattice positions. In fact, the particles actually only can vibrate about their fixed lattice positions. In the liquid state, however, the particles are irregular and random and can move freely within the liquid. They are not bound to the fixed lattice positions in the solid state. And for the gaseous state, it's also irregular and random. The only difference is that the particles are more further spaced as compared to the liquid state. The motion of particles, as mentioned, the solid state, the particles vibrate over their fixed positions. In the liquid state, the particles are free to move about, sliding over one another, while in the gaseous state, the particles are free to move in random directions at high speeds. As a result of the properties mentioned in the previous slide, solids have fixed shapes because the particles have to vibrate over their fixed positions. On the other hand, since the liquid's particles are free to slide over one another, it doesn't have fixed shape. It will take on the shape of the container. Same thing for the gas. The distance between the particles for the solid is very close together, whereas for liquid is slightly more further spaced, and for the gaseous is very far apart. As a result of this, of the distance between the particles, solids have high densities because the particles are very closely spaced, and they're not compressible because you cannot make the particles move away from their lattice positions. For the liquid state, it's also high densities and the particles cannot be compressed. For the gaseous state, however, since they are very, very far apart, the forces of attraction between the particles are very negligible. Hence, it's possible to compress the gaseous state. And in the gaseous state, since the particles are very far apart, they also have very low densities. In the solid state, because the particles are very close together, so the intermolecular forces of attraction between the particles is very strong because of the fact that they're closely spaced. In the liquid state, they are strong, but not as strong as in solid. It's because the particles are more further spaced as compared to that in the solid state. For the gaseous state, since the particles are very, very far apart, the intermolecular forces of attraction that can operate between the particles are very weak. And hence, because of the fact that the intermolecular forces of attraction is very strong, solids have fixed volume, liquids also have fixed volume. You cannot compress them. But for gases, because the intermolecular forces of attraction is very weak, it doesn't have a fixed volume and shape. It will just take on the shape of the container, as well as you can compress it. Okay, so next we'll talk about energy forms. The only type of energies that any substance can have can actually only be divided into two categories: that of kinetic energy and potential energy. So kinetic energy is an energy that particle possesses due to its motion, while potential energy is the energy that a particle has due to its position. Okay, one is due to motion and one is just due to the configuration of all the particles in that state. Okay, so simply if you write it in a mathematical equation, the total energy is the sum of the potential energy. So this is potential and this is kinetic. Okay, so since the total energy is made up of the potential energy portion as well as the kinetic energy portion, when you provide heat to a system, by conservation of energy, the energy cannot just disappear. It must be transferred to the substance. And since the substance only contains potential and kinetic energy, the energy must go into increasing either the kinetic energy or the potential energy of a mixture of both of them. Okay, when you supply heat, it will increase the potential or the kinetic energy of the substance. Similarly, if the particle actually loses energy, energy actually goes from the substance out into the environment, the energy that is lost must come from a combination of the potential and the kinetic energy of the system. So how can we measure kinetic energy? The answer is temperature. So temperature is the measure of the average kinetic energy of a substance. If the temperature of a substance is higher, it will mean that the substance actually has a higher average kinetic energy, vice versa. When you increase the heat energy, when you supply heat energy to increase the kinetic energy of a substance, the temperature of the substance will increase as the kinetic energy increases. Similarly, if the substance loses kinetic energy in the form of heat energy to the surroundings, the temperature of the substance will drop. For potential energy, as we've mentioned before, the potential energy is a function of the configuration of the particles. It's by energy that a substance has by virtue of its position. And it's primarily due to the intermolecular forces of attraction between the particles. And it's easy to understand, if the particles are more closely spaced, the potential energy will actually be greater. Okay, so when you actually use heat energy to increase the potential energy of a system, the distance between the particles will actually increase. And when a substance loses potential energy in the form of heat energy to the surroundings, the distance between the particles will actually decrease. Okay, and if the only thing that changed was the potential energy of the system, that means when the system changes the distance between the particles, it will only affect the potential energy. If the kinetic energy is unchanged, then the temperature of the substance will remain constant. Okay, having said about the kinetic energy and potential energy, we are now ready to discuss heating curves and cooling curves. Okay, so for example, if you start off with a substance in the solid state and you heat up the solid, it will gradually increase the energy. And since temperature is the measure of the average kinetic energy of the system, as the temperature increases, it must mean that the heat energy that is supplied to the solid goes into increasing the kinetic energy of the system. Okay, so at this stage, right, there is an increase in the kinetic energy of the system. Okay, after which you reach the melting point, and when it reaches the melting point and the solid is actually undergoing the process of melting, changing from solid to the liquid state, it will actually go through a period whereby the temperature remains constant. Since temperature is the measure of the average kinetic energy of a system, and if the temperature remains constant, it would mean that there is no change in the kinetic energy for this portion. However, if you supply heat energy, right, the heat energy cannot disappear. So if it doesn't increase the kinetic energy, it must increase the potential energy of the system. And when it increases the potential energy of the system, what it means is that it will basically, the energy that is supplied will be used to overcome the intermolecular forces of attraction of the solid particles, allowing them to separate further to take on the configuration of the liquid state. Now, when the solid has fully melted, it will reach this point, and then now the entire substance is in the liquid state. And as you continue to supply heat, the temperature will continue to rise, and there will be an increase in the kinetic energy of the liquid state. Okay, so the temperature rises, and there's an increase in the kinetic energy. It will then again similarly reach the boiling point, and when it reaches the boiling point, the temperature will remain constant. And since the temperature remains constant, again, there will be no change in the kinetic energy, but the heat supply will be going in to increase the potential energy of the system, overcoming the intermolecular forces of attraction between the particles, and hence allowing the particles to go from the liquid state to the gaseous state. After the liquid state is fully changed into the gaseous state, any further supply of heat will then go into increasing the kinetic energy and thereby increasing the temperature of the gas. So this is how to understand the heat curve. In which instances is there an increase in the kinetic energy, and in which instances is there an increase in the potential energy. Okay, so this is just the reverse cooling curve. So it's not much different to the heating curve. So let me just quickly run through it. From a gaseous state, as it cools down, there will be a decrease in the kinetic energy because the temperature drops. As it reaches the gaseous state, it will start to condense into the liquid state, and there will be no change in the kinetic energy because of the fact there's no change in temperature. However, the potential energy will drop as the particles become closer to take on the liquid configuration. After it's fully converted to the liquid state, the temperature will start to drop, and hence there is a decrease in kinetic energy. It will then reach the freezing point, and then in this region, there will be no change in the kinetic energy, but again, there will be a decrease in the potential energy as the particles from the liquid state come closer to take on the configuration of the solid state. Then when it finally changes on to the solid state, there will be a further drop in the temperature, which means that there will be a further decrease in the kinetic energy of the system. So basically, you can just think of it as running the argument backward from the heating curve. Okay, so as the solid is heated, from its melting point, it gains kinetic energy from heat energy, and as it gains kinetic energy, the temperature of the substance will increase. So this is basically just a summary of what I've explained from the heating curve and cooling curve. Okay, so like during melting, as the solid is heated, the intermolecular forces of attraction between the particles are overcome, and the solid will gain potential energy from the heat energy that's supplied, and it will turn into the liquid state. Since there is no change in the amount of kinetic energy, there is no change in the temperature of the substance. After which, there will be an increase in the temperature as the liquid is heated further. It will gain kinetic energy, and therefore the temperature increases. And then it will finally reach the boiling point. And when it reaches the boiling point, there will be no change in the temperature, so the kinetic energy remains constant. However, the heat that is supplied will go into overcoming the intermolecular forces of attraction between the liquid particles. And the liquid particles will then gain potential energy from the heat energy supplied and turn into the gaseous state during boiling. Okay, so the words in the parenthesis is just the reverse process when you're discussing the cooling curve. Okay, so I hope that clarifies how to think about how to go about understanding the heating curves and the cooling curves. Okay, so this is just the last part, as in finally when you continue heating the gas, the gas will gain kinetic energy and therefore the temperature rises. Okay, so now we are ready to discuss why is it that there is only the topic on the gaseous state, there's no liquid state, and there's no solid state. So the studying of nature involves the use of mathematical models to describe the system. Like for example, in physics, right? If you apply a force, it will result in acceleration, and the equation that we come to describe the application of a force that causes an acceleration is by the mathematical model F equals to ma, which is basically decided through empirical evidence, which is experimental evidence. So if we would like to study the different states of model, we will need, the different states of matter, we actually need mathematical models to describe the solid state, the liquid state, and the gaseous state. And basically, what it means is that we have to model the potential and kinetic energies of the different states accurately. We need to be able to describe the kinetic energies of the particles in the solid, liquid, and gaseous state. And we must also be able to describe the potential energy of the solid, liquid, and gaseous state, the potential energy of the particles in the solid, liquid, and gaseous state. It is possible to calculate the kinetic energies accurately. After all, the kinetic energy is just half mv squared of the particles. However, it is extremely difficult to describe the potential energies accurately. The reason is this. For example, let's consider 1 mole of particles. Okay, like for example, if you have 18 grams of water, which is a very small amount, right? 18 grams of water actually contains 6 times 10 to the power 23 number of water particles. And the potential energy is actually a function of the position of the particles, which means that it is a function of all 6 times 10 to the power 23 water particles. You change the position of any single one water particle, or you change the orientation of the water particle, it will actually affect the potential energy. So you need to be able to describe how the potential energy will vary as the positions of all 6 times 10 to the power 23 particles changes and when their orientation changes. So it's extremely difficult to model this. It's just simply a function that is of too many dimensions. Okay, the dimensions are basically the orientations and positions of the particles. So it's extremely difficult to address the potential energies. And because of the fact, so like I've said, it's extremely difficult to model the solid and liquid states because the intermolecular forces of attraction are significant. The reason for this is because in the solid and liquid states, the particles are actually close enough that the intermolecular forces of attraction actually operate significantly between the particles. Okay, so when we talk about the solid and liquid state, we have to model the potential energy. There is just no way around it. We cannot just ignore the potential energies. We will just get rubbish answers if we try to do a simulation or model, or when we try to model the solid state and liquid states. We have to take into account the potential energies, but that is very, very difficult to do. However, right, because in the gaseous state, right, the particles are very, very far apart, so we can assume that the intermolecular forces of action are small enough that they can be neglected. Okay, so because of the fact they're so far apart, the intermolecular forces of attraction is very negligible, so we don't have to care about the potential energies. And as mentioned before, right, we only have to deal, if the potential energy can be totally disregarded, then we can just only deal with the kinetic energies, and we are able to model the kinetic energies of the particles very accurately, and hence that's the reason why we can study the gaseous state. In fact, in many areas of research, right, a lot of research is still going into modeling the solid and liquid states accurately. Okay, the main difficulty is, as I've mentioned, the potential energies of the solid states and the liquid states. But for gaseous states, we can get away with that because we can assume that the particles are far enough that we can just ignore the potential energies. Okay, so this is just an explanation of why is it that we only study the gaseous state at the JC level, we don't study the liquid states and the solid states. Even if you go to a higher level of study, right, there is no really fixed textbooks, a clear understanding of solid states and liquid states. The reason is just because of the fact that there's no accurate description of it as of today. Okay. Okay, so now we are ready to discuss the ideal gas equation. Okay, so the ideal gas equation is defined as a theoretical gas that is completely described by the ideal gas law. And the ideal gas law is given by PV equals to nRT. Okay, take the pressure of the gas in Pascal, the volume of the gas in meter cube, take the product of it, it will equal to the number of moles of the particles multiplied by the molar gas constant, which is basically 8.314, just a constant number, and the temperature. And I remind you again, it's extremely important when you're using this equation that the temperature is in Kelvin and not in degrees Celsius or in degrees Fahrenheit. It must be in the absolute scale of temperature, which is in Kelvin. Okay, so this is an equation that describes an ideal gas, and it's a theoretical gas. So what are the assumptions of an ideal gas? So the thing is that, although we said that the gas particles are actually very far apart, that we can ignore the potential energy, right? The truth is that the potential energy is actually not zero, right? It's just that we assume that it's zero. So the assumptions of the ideal gas is basically that they have negligible intermolecular force of attraction. We just treat the potential energies to be zero. Okay, and the second assumption is that the volume of an ideal gas is negligible as compared to the volume occupied by the gas. Okay, so for example, right, what this means is this, like for example, if you have a container, and this is, the volume that's occupied by the gas will be the volume of the container, because for the gas particles, it will always occupy fully the volume of the container. However, right, so this is the whole volume of the container, but the thing is that like the volume of the gas is very, very small. Okay, so like the volume of the individual dots, which are the gas particles, is negligible as compared to the volume of the gas that occupies the entire container. Okay, so that's the second assumption. The third assumption is that gases are in constant random motion. I wouldn't go too much into it, but this can be proven to be true using quantum mechanics. Okay, and number 4, it will participate in collisions that are perfectly elastic and of negligible duration. So these are just the 4 assumptions of an ideal gas. Okay, any gas that satisfies these 4 assumptions will basically be accurately described by this equation. Okay, so the thing is that, right, imagine if you have a question and you did a calculation of a real gas using the ideal gas equation, and then the answer that you get is not, the answer that you get from this equation is not the same answer as when you did the experiment on the real gas, right? Then basically what it will mean is that is because the real gas does not fulfill these four assumptions, right? Because the PV equals to nRT is based on these four assumptions. If these assumptions are not true for a real gas, then certainly the answer that you get will not be exactly the same as, the experimental result for the real gas. And which is the assumption that we will always attack when the results do not concur? Okay, the answer is number one. Okay, because as I've mentioned, right, real gas always have a certain amount of intermolecular forces of attraction. It's just that in the ideal gas equation, we throw it away and we discard the potential energy term, and therefore we come to the conclusion that it will be this equation. Okay, so basically whenever the answers don't agree, we will always, the reasoning will always be that one of these some of the assumptions are not true, and the assumption that is always not true that we will always quote is because that the real gas actually have non-negligible intermolecular forces of attraction. Okay, and moreover, right, if you compare two gases, gas A and gas B, and if we see that gas A has greater intermolecular forces of attraction as compared to gas B, right, then it should be understood that the results that you get from this calculation will deviate further away for gas A that has a stronger intermolecular force of attraction. It's because gas A deviates further away from this key assumption of the ideal gas equation. Okay, I hope that makes sense. If it's a bit confusing at this stage, just hang on. When we do some questions, I will just go through this concept again. Okay, so real gas versus ideal gas, like I've mentioned, right? A real gas is defined as a gas which will not always show ideal behavior. It's because the real gas do not fit all the assumptions of the ideal gas. And this is primarily, again, due to the deviations away from the assumptions made in the ideal gas model. Okay, and the extent and degree of deviation from ideal gas behavior will depend on the type of gas. It's basically, right, like it depends on the degree of the intermolecular force of attraction of the real gas. Okay, so if the size of the gas particles is larger, then the volume occupied by the gas particles will be more significant as compared to the volume occupied by the gas. So there will be a greater deviation away from the ideality. And if the size of the particles is, and if the intermolecular forces of attraction between the particles is greater, right, then it will also deviate further away from ideality. Okay, this is basically the more important one. Okay, whether the intermolecular forces of attraction between the particles are strong or not. Okay, so for pressure, right, the way to think about this is this. Okay, like, so for example, if you have this system, right, and then like you have some gas particles inside here. Okay, so let's say, right, you push down on the piston, right? And then like, so when you push down on the piston, what will happen is that the pressure will increase because the volume actually decrease, right? Like imagine if you would take a syringe and then you compress the syringe, right? I'm sure that you understand that the pressure will actually be higher when you actually decrease the volume. Okay, so when you actually increase the pressure, what you actually do is that you actually cause the particles to be more closely spaced. And as we have mentioned, right, if the particles are more closely spaced, then the intermolecular forces of attraction between the particles will be more significant, which will cause it to deviate further away from the assumptions of the ideal gas equation. And hence, the higher the pressure, the smaller the distance between the gas particles. And if the distance between the gas particles is smaller, then the interatomic or intermolecular forces of attraction between the gas particles will become stronger, become more non-negligible. And also, moreover, the volume of the gas particles will become more non-negligible compared to the volume occupied by the gas, and hence, under the conditions of high pressure, the gas will deviate away from ideality. Okay, so again, I've emphasized again, the key picture that you have to hold is that as the pressure increases, the particles become more closely spaced. As it becomes more closely spaced, the intermolecular forces of attraction will become stronger, which will cause it to deviate further away from ideal gas behavior. Okay, because the key assumption of the ideal gas behavior, as I've mentioned again and again, is that there's negligible intermolecular forces of attraction between the particles. For temperature, right, again, it's the same idea. If the temperature is actually lower, right, it will cause the distance between the particles to be closer, because when things decrease in temperature, it actually contracts, right? If the distance between the particles decrease, then it's the same argument. The interatomic forces of attraction or intermolecular forces of attraction will become more non-negligible. And also the volume of the gas particles will become more non-negligible as compared to the volume occupied by the gas, which will cause the gas to deviate further away from ideal gas behavior. Okay, so a real gas behaves most like an ideal gas at low pressures, because at low pressures the particles are more further spaced, and hence the intermolecular forces of attraction will be less significant, more closely fitting the assumptions of the ideal gas behavior. At high temperatures, again, the particles will be more further spaced, and with more further space, it will again have more insignificant intermolecular forces of attraction, which will cause it to fit the assumptions of the ideal gas behavior to a larger extent. Okay, so we've gone through the content for learning outcome A and B. State the basic assumptions of the kinetic theory as applied to an ideal gas. So I remind you, it's basically this, let me go back, these 4 assumptions. Okay, those are the assumptions for an ideal gas. And then explain qualitatively in terms of intermolecular forces and molecular size, the conditions necessary for a gas to approach ideal behavior. So as I've mentioned before, the conditions is of that of high temperature and low pressure. Okay, and the limitations of ideality at very high pressures and very low temperatures is because at high pressures and low temperatures, the particles are very closely spaced, and if it's closely spaced, the intermolecular forces of attraction will be significant, and the key assumption of the ideal gas behavior will break down. Okay, so I hope that you are able now to answer these 2 learning outcomes. And in the next video, we'll look at some past year A-level question that specifically test on these 2 learning outcomes. So if you like this video, just hit the like and subscribe button and stay tuned as we go through some of the questions from the past year A-level that test on these 2 learning outcomes. So thank you for tuning in and see you once again.